Climate regulation is complex, but it is based on relatively simple and easy to understand feedback loops. In a feedback loop, an action triggers a response that either amplifies or reduces that action. The two basic feedback loops are positive and negative ones. A negative feedback loop is self-inhibiting. Two processes mutually inhibit each other, promoting stability. For example, a thermostat turns on the air conditioning when it gets too hot and turns it off when it cools down. On the other hand, a positive feedback loop is self-reinforcing. Two processes mutually amplify each other, potentially spiraling out of control. For example, when a microphone gets too close to a speaker, the sound gets louder and louder in a loop of increasing noise. I will now describe some of the negative and positive feedback loops that regulate our climate. Understanding these feedback mechanisms is essential for comprehending how the Earth's climate system responds to various factors, both natural processes and human activities. Negative feedback loops counteract changes in a system, helping to stabilize it. In the context of climate and atmosphere, negative feedback loops work to reduce the effects of warming or cooling, maintaining a balance that prevents extreme fluctuations in temperature and other climatic conditions. Earth's climate stability, crucial for supporting life, has been maintained over billions of years despite the Sun becoming significantly stronger since Earth first formed. This remarkable stability is largely due to the atmospheric CO2 thermostat, a negative feedback system that regulates CO2 levels in the atmosphere through weathering, plate tectonics, and volcanic activity. Here's how it works. Rainwater dissolves atmospheric CO2, forming mild carbonic acid. An increase in CO2 levels leads to a rise in temperature and precipitation, which enhances the weathering of rocks. These weathered rocks are transported to the ocean as carbonate minerals, effectively removing CO2 from the atmosphere. This removal of CO2 lowers its concentration in the atmosphere, resulting in a cooler and drier climate, which in turn slows down the weathering process and the removal of CO2. This slow but persistent cycle acts like a thermostat, adjusting CO2 levels that regulate global temperatures. This thermostat kept conditions on Earth compatible with life for billions of years, thus enabling the evolution of complex forms of life. In spite of climate fluctuations during Earth's history, it never got too cold, neither too hot for at least some forms of life to persist. However, before we get too enthusiastic about this loop solving our current predicament, we must realize that this is a very slow process, taking hundreds of thousands or even millions of years. It will not save us from the surplus CO2 we are currently pumping into the atmosphere. A second, faster negative feedback loop, removing CO2 from the atmosphere, is carbon sequestration by plant photosynthesis. In some ecosystems, temperature rise and increased CO2 concentrations lead to more favorable growing conditions and/or longer growing seasons. Increased vegetation growth enhances carbon sequestration in plants and soil. The reduction in atmospheric CO2 levels can mitigate the greenhouse effect, leading to climate cooling. This forms a negative feedback loop, where warming initially leads to enhanced carbon sequestration, which then reduces the warming effect. This is the rationale behind planting trees to fight climate change. However, this feedback loop works only to some extent under certain conditions and in specific regions, as factors other than CO2 often limit plant growth. Moreover, high temperatures stress many plants. Now, let's look at the positive feedback loops that are amplifying climate change and warming, often leading to more extreme changes in climate conditions. So they are not really positive, and the colloquial name vicious cycle suits them much better. The ice albedo feedback is a classic example of a vicious cycle in the climate system. Ice and snow have high albedo, meaning they reflect incoming solar radiation back into space. When global temperatures rise, ice and snow melt. The reflective ice and snow are replaced by darker surfaces such as ocean water or land, which reflect less radiation and thus absorb more solar energy. This additional energy increases temperatures further, causing even more ice and snow to melt. This creates a self-reinforcing vicious cycle where warming leads to more warming, accelerating the effects of climate change. Indeed, anthropogenic climate change is causing temperatures to rise in the polar regions considerably more than in regions closer to the equator. A second extremely worrying self-reinforcing vicious cycle is permafrost thawing. Permafrost, the frozen ground found in polar regions, contains large amounts of organic carbon. When permafrost thaws due to rising temperatures, the organic matter begins to decompose, releasing the potent greenhouse gas methane. The release of methane further enhances the greenhouse effect, leading to additional warming. This warming causes more permafrost to thaw, releasing even more methane. A third and final vicious cycle is the water vapor feedback loop. Water vapor is the most abundant greenhouse gas in Earth's atmosphere, and its concentration is directly related to temperature. As global temperatures rise, more water evaporates from Earth's surface, increasing the concentration of water vapor in the atmosphere. Every 1 degree Celsius rise allows the atmosphere to increase its water content by approximately 7%. Since water vapor is a greenhouse gas, its increase leads to further warming, causing even more water to evaporate, creating a self-reinforcing vicious cycle. Understanding feedback loops is crucial for predicting and managing the impacts of climate change. Positive feedback loops, in particular, are of major concern because they have the potential to push the climate system past critical thresholds, leading to irreversible changes. These could trigger cascades of effects that accelerate global warming, making it ever more challenging to stabilize the climate. Negative feedback loops, while stabilizing, are not always strong or fast enough to counteract the effects of positive feedbacks and the rapid, large-scale CO2 emissions from fossil fuel burning. Unfortunately, this leads to the significant climate changes that I will describe in the next video.